Dear colleagues, dear friends, welcome to our seminar on optimization. Today's speaker is Bruno Lourenço from Tokyo. He's a Brazilian, but he's affiliated with the Institute of Statistical Mathematics in Tokyo. Bruno Lourenço received his PhD in mathematical and computing sciences from Tokyo Institute of Technology in Japan, under supervision of Professors Fukuda and Tsuchiya. And after his PhD, he was assistant professor at Seiki University. He was then assistant professor at the University of Tokyo. And starting with April 2020, he's associate professor at his current academic institution. I had the impression, Bruno, that you spent some time in Hong Kong as well, but this information I wasn't able to find in your CV.
Okay. It's just for a short visit.
Okay, a short visit. So he is working on several topics in optimization. So I would say that he has a preference, a favor for theoretical topics in optimization. So we are very glad that he accepted our invitation, in spite of unusual time to give a scientific call, a scientific talk. So again, thank you for being with us, Bruno. You have 45 minutes for the talk.
Okay. So first, I'd like to thank you for the organizers of this very nice meeting for the invitation. And today I'm going to talk about error bounds and facial residual functions for conic linear programs. So this talk is going to be based on several works I did with my colleagues, so Scott Lindstrom from Curtin University, Tin Shan Liu from Tokyo Institute of Technology, Tin Kei Pong from Hong Kong PolyU, Vera Roshina from the University of New South Wales, and James Anderson from Monash University. So I'd like to start the talk by considering the following hypothetical situation. So suppose I'd like to solve some nonlinear programming problem, minimizing fx subject to hx equal to 0. Suppose also that I use my favorite solver to try to solve this problem, and the solver returns to me some solution x star. Furthermore, the solver also tells me that the KKT conditions are satisfied to 10 minus 6. And it also tells me that the norm of hx star is less or equal to 10 to the minus 7. So then I think there are two very natural questions that one might wonder. So the first is, so is x star indeed close to the set of optimal solutions? So the solver is telling me that the KKT conditions are satisfied to 10 minus 6. So does this actually imply that x star is close to the set of optimal solutions? Or a bit less ambitiously, I might wonder whether this condition here so implies that x star is close to the set of feasible solutions. Now, you might have guessed that because I'm starting my talk with this, I'm probably setting the ground for some mischief, and you won't be wrong. So next, I'd like to introduce an example developed by Stum, so this more than 20 years ago. So we consider this for the following semi-definite feasibility problem. So I want to find some 3x3 symmetric matrix having this shape and being positive semi-definite. Now, because I have a 0 here, this forces these entries to be 0. So this is 0. And then because x33 is 0, this is 0. So the set of feasible matrices of this feasibility problem are matrices of this form. Now, I consider the following sequences of points. For every positive epsilon, I define this family of matrices. Sorry, so for every epsilon, I define this 3x3 matrix. And looking back at this problem, I have two types of constraints. So I have some affine constraints and a positive semi-definite constraint. So I require that x22 be 0, x12 is equal to x33, and these three constraints are enough to express this problem. Suppose also that we measure the violation of the constraints by this formula. So this red part here corresponds to the affine part of the constraints, and this part here corresponds to the positive semi-definite part. And I would argue that this is reasonable because the residual is only 0 if and only if x is feasible. Now, although this residual sounds reasonable, something funny happens. So with respect to this way of computing the residuals, this x epsilon does not seem to be a bad point because this constraint is satisfied, and you can do some computation to check that this matrix is actually positive and definite. So the only constraint that is violated is this one. So the residual is epsilon. However, if you actually compute the distance to the feasible set, it should be at least this, the fourth root of epsilon. And the reason is because, if you recall, the feasible matrices have this shape. And because we have this term here, the distance to the feasible set must be at least this. So the conclusion is, for example, if you have epsilon to 10 to the power minus 4, the residual is telling you that you are 10 to the minus 4 close, but if you actually compute the distance to the feasible solution, this is at least 0.1. So there is some difference in order between these two things. So going back to the questions I asked in the beginning, so the answer is that not necessarily. And even more dramatic, there is an even more dramatic kind of failure that can happen. So it can even happen, for example, that you can drive the residual to 0, but it's still not the case that this distance to the feasible set is going to be 0 as well. So what is happening is more or less this. So when you solve an optimization problem via solver, typically you input the constraints one by one. So you have a bunch of equality constraints, you might have a bunch of inequality constraints, and then you might have some conic constraints. And what happens is that solvers typically can only compute the residuals with respect to these individual functions here. And this is in the literature is sometimes called the backward error. And of course, sometimes you might take some average of these, you might square these things, do a bunch of computations. But the fact is that the true distance to the feasible region is almost never computable. And this is what's sometimes called the forward error. And in the previous example that I showed, so for example, the backward error is this residual that you can actually compute, and the forward error is the actual distance to the feasible set. So the key point I'd like to emphasize through this example is that in general, these things do not have the same order. Forward error doesn't necessarily have the same order, the backward error. And this already happens for feasible sets. So of course, if we look at what happens for optimal sets, the same phenomenon might happen. So a small KKT residual does not imply that the point is close to the optimal set. But I would argue that, for example, when someone solves a problem via some software, that person is actually interested in this, the forward error. So I think it's important to understand how to, in fact, relate the forward error and the backward error, even though they do not necessarily have the same order. And this is precisely what error bounds give us. So error bounds provide ways of relating the forward error and the backward error. And in this talk, I'd like to talk about some results for problems involving cons. So far, are there any questions?
I have a question, Bruno. So yes. The nomenclature forward error, backward error is this something which is already established a standard in the literature, or is it more your notion, or are these more your definitions or your notions?
So this was used by Stum himself. So he wrote this paper on error bounds for semi-definite. He used this kind of nomenclature. So I think this actually comes.
Okay.
I think this might. Oh yes, I see there is another.
Manuel.
Yeah, my question is sorry for the interrupt, but I'm wondering. So is in the paper I forgot about the paper. I have seen it before, but I forgot what the argument was. So why are we interested in a forward error? So the backward error is something which is basically saying how far, what is the violation of the constraints. And we could be satisfied with a violation of 10 to the minus 4 by the constraints. We could view the decision as something acceptable. And then we don't care about how far we are. So there must be a reason why we should look at the forward error, of course. But I cannot figure out quickly about this.
Okay, so I can give. So this is actually I pretend to talk this a bit later in the talk. But typically, for example, when you want to prove some convergence rate results for problems, for feasibility problems, you typically need to know how the forward error and the backward error relate. So, does this answer the question? Okay. So if I have time, I'll show some application of these things later. But still, I would say that not many people. No, I would say like this: not all users of optimization software are necessarily aware of this distinction. So I think it's important to clarify this. But okay, let me continue a bit more. So in this talk, I'll mainly deal with this kind of feasibility problem. So I'm going to consider the feasibility problem over a convex cone. So I have K, a closed convex cone contains some space, L, a subspace containing this larger space, and A, some point, in such a way that L plus A is an affine space. So my feasibility problem is the intersection of an affine space and a cone. And I think there are very natural three quantities that we could define. So for example, we could think about the distance to the affine space, the distance to the cone, and the distance to the intersection. And I believe a very fundamental question is how can we estimate the distance to the intersection by using the individual distances? And in this nomenclature that I just mentioned, the backward error is thus, for example, could be the sum of the distance to the individual sets, and the forward error is the distance to the intersection. I think there is a comment. Okay.
Okay. Yes. So this gave an explanation. Okay, thank you.
And yeah, so here's just a simple example. This is still an example that is relatively favorable because both sets are polyhedral, but you can see that this is very close to each of the individual sets, but it's actually quite far from the intersection. So this is a very subtle question. Now, I've mentioned error bound in a very general way, and I'd like to next introduce a family of error bounds that appear a lot in the literature. So it is called the so-called Hoderian error bounds. So suppose you have two closed convex sets, and we say that they satisfy a Hoderian error bound if for every bounded set B, you can find some constant, positive constant, and some exponent such that you can go restricted to this bounded set, you can upper bound the distance to the intersection by a constant times the sum of the individuals distances to this power, a gamma b. And if it happens that you can select the same exponent for all the p's, for all the bounded sets, this bound set to be uniform. And if the bound is uniform with gamma equal to 1, this is what's called a Lipschitzian error bound. Now, I'd just like to review some conditions that imply this kind of error bound. So for example, this is a very, I don't know where this was proved first, but it's well known that if you have two sets that their relative interior, two convex sets whose relative interiors intersect, then you have a Lipschitzian error bound. And if you have C1 and C2 polyhedral sets, then this you also have a Lipschitzian error bound, and this is also called the Hoffman's lemma. Actually, Hoffman's lemma is a bit stronger than this statement, because Hoffman's lemma states that not only the error bound is Lipschitzian, but this error bound is global. So you can find a constant that works for every vector. So actually, it's even stronger than this, because there is some conditions on the constant, but never mind. And for example, if you have C1 a polyhedral set and C2 an arbitrary convex set, and if C1 intersects the relative interior of C2, you also have a Lipschitzian error bound. And Sturm's error bound is the following result. So if you have an affine space and you have a C2 is the post-semi-definite cone, then a uniform Hoderian error bound holds. Now, the remarkable thing about Sturm's error bound is not only the fact that a uniform Hoderian error bound holds, but the fact that Sturm showed how to compute this exponent in a tight manner and connect this to facial reduction. So I was very inspired by this work. And I tried to extend Sturm's results to other families of cones, and I've been working on this with my colleagues. So what I'm going to show next is how can you prove error bounds for general cones beyond the post-semi-definite cone. But an important property is that I like these error bounds to be as tight as possible. And what I'm going to talk next is based on these three papers. Now, I'm not going to lie, these papers are a bit long. So this one is almost 50 pages. But the good news is that they are more or less like 30%, 50% framework. So if you only want to understand the framework and the basic idea, you can more or less read just half of each paper, and the rest is computation of examples. So yeah, perhaps not that bad. And oh, I see there is a.
I'm sorry, just a quick question. So all these bound, even in the most favorable cases of a uniform Hoffman bound, there is always a dependence on the dimension, right? Or
yes.
Because you mentioned the constant, but it's always depending on the dimension, also the constant.
Yeah, so in the case of Hoffman's error bound, yeah, it appears because it depends on the matrix A.
Yes, and therefore it encodes the number of columns of the matrix, right?
Yeah, so it appears like this, yes.
Yes, so, okay. And so uniformity has nothing to do with independence of dimension.
Yes, this uniformity just means that the exponent is the same.
The exponent is the same for all B.
For all B, yes.
But it can depend on N.
It can depend on, but because in this setting here, C1 and C2 are, yes, it can depend on n, yes.
On the embedding dimension for C1 and C2, the minimal something like this. Okay, thank you very much.
So this, I think, so for example, C1 could be embedded, could be, for example, it could be isomorphic to some C3, and this could be embedded in some higher, it could be embedded in some higher dimension. But my understanding is that the dependency of dimension is only with respect to the affine how of C1, right? So, okay, so even if you put this in a larger space, you only need to look at the dimension of the affine how.
Okay, thank you. Some natural minimal embedding space or something. Thank you.
Thank you for the question. So yeah, I already said that this stuff is long, but not that long because you can read just half to get the framework, and then yeah, okay. And so okay, so now before I show how to obtain the zero bounds, I suppose that most of you know about this stuff, but just in case, I'd like to review a bit. So because it's going to appear a lot. So just to be clear, when you a face of a cone is a set satisfying this property. So whenever x and y belong to K, and their sum is in F, then x and y belongs to F. And of course, this must be a closed convex cone to begin with. And in order to get error bounds for arbitrary cones, we need two ingredients. So the first ingredient is the following observation. So we have here our conic feasibility problem. And if it turns out, so this doesn't necessarily satisfy a constraint qualification. So meaning, for example, it's not necessarily the case that some condition like this or some condition like this holds. If some condition like this holds, then we would have a Lipschitzian error bound, but it doesn't in general. So the idea is that we'll try to find some face that does satisfy a constraint qualification. So we try to find some F such that when you substitute K by F, we get the same feasible set, and the affine space intersects the relative interior of this. So if this happens, then by the result I just mentioned, for every bounded set, we have this kind of error bound. Now the detail is that this is not an error bound with respect to the affine space in K, because instead of K, there is F here. But this is very close, and this gives us a hint on how to proceed. So this strategy is more or less like this. We want to bound the distance to the intersection using the individual distances. So we try to find a favorable face for which, when you substitute K by this F, you get the same feasible set, but this affine set, the underlying affine set, intersects the relative interior of F. Then we get a pseudo error bound, because it's not a proper error bound, because we have F here instead of K. However, we can try to somehow upper bound this distance by something that depends on K and the distance to the affine space. And then if after we've done that, it's just a matter of plugging this back here. So the first question is, okay, how can I find F? And it turns out that there is a very nice and simple way of finding F. So you can do this in a recursive manner. So we want to find some F satisfying these two properties. So the idea is we start with F1 equal to K, and we ask ourselves, does this satisfy the condition we want? If it does, then we finish. If not, we invoke a separation theorem. And I think I'm going to skip some of the details, but the separation theorem will give us actually a supporting hyperplane of the cone. And when you take this intersection, you'll find some smaller face that you can go back and repeat this process. Now, of course, for the people who know this is nothing but the facial reduction algorithm originally developed by Boa and Wolkowitz. And there is this thing, I like to call this the facial reduction theorem, that essentially says the following. So whenever you have a feasible conic linear problem, you can find a chain of faces that satisfies some technical conditions. This is not very important moment, but the important detail is that this chain of faces ends with a face that satisfies the two conditions that we need. So when you intersect with the affine space, we get the same feasible region and a constraint qualification is satisfied. Now in the paper, we use a slightly more refined analysis based on this paper, but the idea also works with the classical facial reduction algorithm by Boa and Wolkowitz. And of course, several people have worked on this, like Gabor Pataki have several works on this, and also Waki and Muramatsu. Okay. So now I'm going back to the general strategy. So as a reminder, we want to bound the distance to the intersection using the individual distances. And the idea was that we want to find some good face that satisfies some constraint qualification so that we can invoke this error bound result that we know. Now and then the next step will be to try to upper bound this using the distance to K and the distance to the affine space. But the good thing is that the first step is already done. We already know how to find the face F. So it's through facial reduction. Facial reduction will end with a face satisfying what we want. Now, the gradient tool is something we developed, which is called one-step facial residual functions. So what is a one-step facial residual function? So one-step facial residual function is constructed as follows. You have a K, a closed convex cone, as a Z belong to the dual cone, and a function psi kz is said to be a one-step facial residual function if it satisfies this inequality. So the meaning of this is this: whenever we have a point x such that its distance to k is less or equal than epsilon, and its inner product with c is less or equal than epsilon, then this function provides an upper bound to the distance to this intersection here. So so notice that if epsilon equals 0, then distance xk this is less or equal than 0. So this means that x belongs to k, and then this xc is less or equal than 0, but since x belongs to k, this will be also a non-negative. So this belongs to this. So when epsilon equals to 0, if this inequality implies that x already belongs to the intersection. So the one-step facial residual function that gives us an upper bound when epsilon is greater than 0. And this upper bound can only depend on two things, can only depend on this epsilon and the norm of x. Now, this was the last ingredient. So as long as you are able to compute the one-step facial residual functions, you are able to upper bound the distance to some face using these two quantities here. Now I can go to the main result, which is a bit technical. So I think I'm going to show only the good parts. So what it says is this. So we have a K, a closed convex cone, with no empty intersection. Then for every bounded set, we have that whenever you are epsilon close to each individual set, you can upper bound the distance to the intersection by some quantity like this. And this phi here is a composition, is a special way of composing these functions. It's a composition of one-step facial residual functions. So let me show an example. Okay, so perhaps I should stop now. Are there any questions? If not, then I'll continue. So I mentioned that, so you can see that the key point here is how to compute these one-step facial residual functions. And for example, we computed these one-step facial residual functions for the case when K is a symmetric cone. So this includes, for example, positive semi-definite matrices, second order cone, and direct products of them. And it turns out for these for this family of cones, the one-step facial residual functions look like this. And if you plug in this one-step facial residual function into this result and do some simplifications, what you can conclude is that there is some gamma, such that for every bounded set, we can find some constant such that this Hölderian arrow bound holds. And the nice thing is that this exponent, this gamma here is connected to the number of facial reduction steps. And the reason is that here is where we find our special phase through facial reduction. So at each step, we get one step facial residual function, and then we compose them L-1 times. So each one of these times corresponds to one facial reduction step. So this is an extension of Sturm's arrow bound for the case of arbitrary symmetric cone. If you are familiar with Sturm's arrow bound, you know that it appears a tower of roots. And this is one way to explain why a tower of roots appears as the exponent, because each facial reduction step, you are putting one square root here. Now, I'd like to show two more examples. So the next example I'd like to talk about is about the p-cones. So we have x bar p is represents the p norm, and we define the p-cone like this. So it's an n+1 dimensional vector such that x0 is greater or equal than the p norm of the rest. Now, I think most people are familiar with the case p equal 2. So this corresponds to the second order cone. So many of you might wonder how different this can be from the second order cones, and the answer is that this object can be very, very different. This is explained, for example, in this paper. And the one-step facial residual functions for this object are like this. I think I'm not going to explain all the details, but the interesting thing about this is that the actual exponent then depends on the number of zero components that a certain vector that exposes the face that contains the feasible region has. So it's a bit more complicated than what happens for symmetric cones, where in all cases you can take the exponent just to be half the exponent of the one-step facial residual function. So this is more intricate. So the conclusion is that for the p-cones, we have Hölderian arrow bound, but the computation of the exponent depends on the number of zeros that a certain vector has. And another interesting thing we're able to show is that the result is tight. So these exponents cannot be improved. And finally, one application of this is, for example, when you are interested in doing least squares with p-norm regularization. So you have a least square problem, and then you add some p-norm regularization. And one thing you can do, you can represent this as a conic linear problem. So you can, I think I'm also going to skip the details of this, but the point is that you can transform this into a conic linear problem. And then you can express the optimal set as the intersection of an affine space and a cone. So now we can express the optimal set of this problem as an intersection of affine space and a cone for which we know how to compute error bounds. And it turns out, and this is also something I'm going to skip the details, that you can leverage the error bounds for this problem to an error bound for this function itself. So, and these also use some results developed by Yu, Lee, and TK Pong. And so if you are familiar with the KL property, one conclusion that you can get from this stuff is that if you have X star an optimal solution to this problem, under a mild condition, this G satisfies the KL property with exponent 1 minus alpha, where alpha is like this. So the final example I like to show is about the exponential cone. So the exponential cone is a cone defined like this. It has many interesting applications: entropy optimization, logistic regression. There's a very nice survey that you can see about this stuff. And although this might seem a relatively exotic object, is actually widely available. So for example, Mosaic commercial, very good commercial solver implements it. And we work also in trying to find error bounds for the exponential cone. And what we found out was that if you have a problem over the exponential cone, 4 types of error bounds are possible. So you have Lipschitzian error bounds, you have Holderian error bounds, but 2 new classes of error bounds appeared. So we found something called an entropic error bound. So the entropic error bound has this name because this function appear here. So this is just an entropy function. And also we found an example of logarithmic error bound. So where the right-hand side is controlled by some logarithmic function. And again, we show that these results are tight. You cannot improve on the choice of functions. So as crazy and weird this seems, you cannot improve on the choice of functions. This is something we have to live with. And what I like to say is that there's more stuff in the papers. I skipped a lot of stuff. So for example, how to deal with direct products, many techniques for obtaining the facial residual functions for proving tightness, and so on. Now, let me just ask one thing. How am I doing with time?
Great. 10 more minutes.
Okay, so I think I can go to the bonus content of this talk.
Yeah.
So this is actually related to Professor Bones' question at the beginning. So, okay, why this stuff is useful? So because error bounds provide information on the speed of algorithms. So for example, suppose you have 2 convex sets and you do cyclic projections. So these are very well-known results. Well, the first one is very well-known, that if you have a Lipschitzian error bound, then you have linear convergence. And if you have a Holderian error bound, you have a sublinear convergence, and the alpha depends on the exponent that appears in Holderian error bound. So a very nice paper where you can see this stuff is this one by Bowen, Lee, and Tam. Now, as you see, so these 2 things are, this is a Lipschitz and a Holderian error bound, but as I've just explained, sometimes you need, when you have problems involving exponentials, logarithms, sometimes weird stuff happens. So you need entropic, appears entropic error bounds, logarithmic error bounds. So I work with Tianxiang Liu on trying to obtain convergence rates and convergence rate results that appear also when you have exotic error bounds. So we developed this notion of consistent error bounds. So a consistent error bound function is this. So it's a function phi such that for every x, phi receives as input the maximum among the distances to the individual sets and outputs an upper bound to the distance to the intersection. Now, these two conditions here only say that this function must be monotone with respect to each argument and so on. So the important thing is this first condition here. And all the error bounds I mentioned in this talk, so Lipschitzian error bounds, Hölderian error bounds, entropic error bounds, and logarithmic error bounds, they are covered under this notion of consistent error bound function. And we prove an abstract convergence result that's more or less like this. So suppose you have a bunch of convex sets, and you have a consistent error bound function. And now suppose that you have a sequence generated by some reasonable algorithm. I'm not being very precise here, but you can think, for example, it's cyclic projections. It would be a typical example of an algorithm that will be reasonable. And then we apply a bunch of transformations to this function. We put square root inside, takes power outside, then we compute some generalized inverse, and then take the reciprocal, and then apply some integral, and just for good measure, we invert this. But what we are able to show is that if after you're doing all these operations, you're able to compute this will actually give you an upper bound to the distance to the C, will give you an upper bound of the distance to each iterate to the set C. Now, of course, when someone sees this, a very natural question is that, okay, this looks hard. So is this practical? And the answer is that if your underlying error bound is Hölderian, this can be computed in Hess closed form. And if not, there is something called Karamata theory and functions of regular variation. If you combine, if your underlying error bound is a regular varying function, you can give some upper bounds based on this body of theory. So I think I don't have enough time to explain the details of this, but we were able to give convergence rates even under the exotic error bounds that I mentioned to you. So for two sets, our result tells us that when you have a consistent error bound for these sets, you get this bound for the iterates. And if the underlying entropic error bound, if the underlying error bound is entropic, you can show that the convergence rate is in a sense almost linear. So this means that this convergence rate is faster than any sublinear. And this means that the convergence rate is lower than any linear convergence rate. And for the logarithmic error bound, we were able to prove that the convergence rate is logarithmic. So just to be a bit more concrete, so for example, if we have a problem if we have a problem involving the exponential cone, and we apply cyclic projections to solve this, and the underlying error bound is entropic, then this result says that the convergence rate is almost linear. So it's something between sublinear and linear, better than any sublinear, but worse than linear. And for the logarithmic error bound, you can prove that the convergence rate is logarithmic. Now, I think I have 2 minutes or so.
Yes, 2 minutes is fine. Yes.
Okay. So the first version of this paper, of this framework, was based on amenable cones. So I think I have to say just very briefly what's an amenable cone. So amenable cone is a cone that has an error bound inside its spatial structure. So it essentially says that for every face of K, you can find some constant such that this holds. So this is an error bound condition on the facial structure. And although this sounds strange, actually many cones are amenable. And you might wonder how this compares with the usual exposedness properties. So for example, we have facial exposedness, we have niceness, we have projectional exposedness. And this is something, and since I think Professor Wolkowitz is here, I should make sure that people are very creative about naming this stuff. So for example, there is something called devious cons. This was given by Tunsel and Wolkowitz. So you can say, for example, that the positive semi-definite matrices are both devious and nice. But never mind. So the comparison between these properties is like this. So projectional exposedness implies amenability, which implies niceness, which implies facial exposedness. There exists a 4D cone that's facially exposed but not nice. And together with Vera, Roshina, and James Saunderson, we show that there exists a 4D cone that is nice but not amenable. But in 4 dimensions or less, amenability implies projectional exposedness. And recently, we were able to prove that hyperbolistic cones are amenable. So this improves the previous best result that was due by Renega. So Renega showed in 2005 that hyperbolistic cones were exposed, but we recently were able to show that they are amenable. So this implies, for example, that they are nice. And this EPBR is that because this means essentially proved by the referee. So the referee of one of my papers essentially proved this for me. So this is a way to say thank you to the referee. And I think with that, I can mention 2 open questions. So the first open question is there an amenable cone that's not projectionally exposed? In order for this to happen, dimension must be at least 6. And which cones are projectionally exposed? Okay, I think I'll be able to go through all the bonus content of my talk. Thank you very much for your attention.
Thank you very much for the talk. Yeah, hopefully the referee is attending the talk, or he will just watch the YouTube video. So, are there questions? Oh, Henry?
Oh, I can't hear you.
We cannot hear you.
Do you hear me?
Yes, now.
Yes,
Yes.
now I hear you, yes.
So I was wondering if you could say something that about the error bounds. Examples that you show, in some sense, what it's saying is you actually have a bad model for the problem. If you change the model, then the error bounds change.
Yes, that's true. Yes, so the error bound is depends very much on the way that on the algebraic expression of the problem. So even, for example, in the first example by Stum, so here what's happening is that in reality this is just a 1-by-1 SDP, so just a linear program, but we are writing this in a very degenerate way. So this kind of thing, this kind of phenomenon can happen. But the thing is that I think this is very difficult to detect especially, for example, if your instances are non-generic, or if they arise, for example, from some SDP relaxation or something like that, of some combinatorial problem, these strange things might happen. I'm not sure if this answers the question.
Maybe?
Oh, I think I cannot hear you.
We cannot hear you. And, yeah, let's take first question in the chat. So Nguyen Dong Yen is asking if there are any concrete applications of these results to collinear programs of the standard format.
Yeah, so for example, there is, so for example, this is, I think, is important applications, or an important application. So for example, sometimes you might want to solve a conic feasibility problem via say cyclic projections or something like this. Or for example, you might solve your conic linear optimization problem with a solver, and then you might want to improve a bit the feasibility of it, and then you might apply some cyclic projection algorithm to it. And then the error bound will give you what kind of convergence rate you can expect. So this is one way how these things can be used. And I think many questions related to convergence analysis of the algorithms depend on the kind of underlying error bound.
So I have a question in the chat. Can you say something about your results for singularity degree greater than 2 compared to polyhedral?
So are you talking about the symmetric cone, or you're talking about in general? So if it's in general, so this
Just in general.
In general, okay. So this result works for arbitrary singularity degree. There is no requirement that the singularity degree is 1. So this works for in all situations. So so this L-1 here is the number of facial reduction steps. So you can just say replace this by the singularity degree, for example. So this works in general. But can it be applied for singularity degree 2 in practice? So the thing is that the singularity degree, there is some upper bounds, right? So for example, the singularity degree of some system, for example, if this case a symmetric cone, this is going to be upper bounded by the rank, right? So if you apply if you have a reasonable upper bound to the singularity degree, then you can still get something. And now, of course, to get a good upper bound to the singularity degree, then you have to do a very tight analysis on the number of facial reduction steps. That was one of the things I tried to do with Professor Muramatsu and Professor Scheer in this work. Try to be as tight as possible on the number of facial reduction steps you need to regularize stuff.
So are there other questions? Well, I will have a naive question, Bruno. So could you please go to one of the, let's say, one of the basic statements on, like the one involving 2 sets with non-empty intersection of the relative interiors? I have here curiosity. Okay, so let's take the Lipschitzian case and also the third one. So the technique for proving such inequalities, I mean, probably I was aware of this, but is this would it be possible to do it by using, let's say, conjugate calculus, by by proving that the let's say the opposite inequality is true for the conjugate of the two functions on the left and right hand side, and they use some duality theory and then the constraint qualification.
I think typically what I can say is this. I think the typically this proof starts by, okay, because you first consider this case. This case is easier when it's actually interior.
Okay.
And then you pick you pick a point in this section, so you can find a ball that's contained that's inside both sets, and that is more or less the starting point.
Okay.
I don't know if you can do this analysis from the dual the dual side, but okay, yes, there is something you can do from the dual side, because if I'm not mistaken, so this is the
Yes, this is what I had in mind. Yes, I mean using the conjugate calculus, but of course,
there is a paper by Bowline. Let me tell you the exact name of the paper. So it's called it's by Bauschke, Bowline, and Lee. So it's called Stronic. Okay, I'm going to put in the chat. It's this paper. So there is some arguments that go in this way, that you express the distance function as some informal convolution, and then you do some.
Just write the dual statement of this statement and try to prove the dual one, which is so probably easier to prove.
I should. This is something I should have mentioned, perhaps, is that Lipschitzian narrow bound sometimes goes by the name of bounded linear regularity.
Yes. Yeah.
And this is also related to subtransversality.
Yes, of course. So this would apply only for gamma 1. I mean, I guess otherwise, yeah. Okay. Good. Thank you. Are there other questions? So let us stop here. Thank you, Bruno, for a very interesting talk. So these are very impressive results. Yes, so we'll post the slides in the video on our website, and the video will be posted also on the YouTube channel of our seminar. So I wish all of you a good week. So Bruno, have a good night. And see you next Monday. The speaker next Monday will be Matt Pilanci from Stanford University. All the best. See you next Monday. Goodbye.
Bye.